In this set of notes, we are going to learn how to sketch functions using all the things that we've done in 4.2 to 4.5. So basically, sketching graphs using all the calculus that we've learned. You did something similar to this in Algebra 2 when you learned how to graph quadratics. You would get your vertex, you'd get your x-intercepts, your y-intercepts, depending on what form you were in. You would graph your quadratic functions a specific way. This time around, we are just using all of the calculus techniques that we've learned to graph any type of function, not necessarily quadratic. The first thing that we're going to do is we are going to figure out our function's domain. Then we are going to find our critical points. How do we know where those are happening? It is where our derivative equals 0 or does not exist, but that x value is in the domain of your function. A lot of people have been forgetting to check this scenario. You need to make sure that you are checking the does not exist scenario, because I have given you functions where there wasn't a critical point where your derivative equaled 0, but where the derivative actually did not exist. Doesn't happen as often, but you need to make sure that you're checking that. All right, and then where is your function increasing? Where the derivative is positive, and decreasing is where your derivative is negative. So with these two things, with your critical points and your increasing, decreasing, that would be your first derivative number line or your first derivative test. Points of inflection, where did those occur? Where second derivative equals 0 and changes sign. Because remember, points of inflection are where the concavity changes. And if you don't have the sign change, then it's not a point of inflection. Your function is going to be concave up where your second derivative is positive, and concave down where your second derivative is negative. These two things, you can do your second derivative number line or your second derivative test. Then you want to find any local extrema. There are two different ways that you can find your local extrema, so write which one down that you would prefer. You could use your first derivative test with your critical points, and it would be where your critical points go from positive to negative for a local max, and then negative to positive for a local min. Or you can use your second derivative test on those critical points. If you plug your critical point into the second derivative and you're finding out that you're in a concave up interval, then you know that you have a local min, and vice versa. Concave down would be the critical points occurring at a local. So I'm going to write both of those scenarios down. You pick one, and movie magic will appear on my screen in 3, 2, 1. Moving on to some of our other things that we don't necessarily need to use calculus for. The end behavior we do, but the holes and vertical asymptotes not so much. So for a hole, this is really only going to happen if you have a rational function. And it would be specifically where the factors cancel out from the numerator and denominator. So that'll get you your x value. Because we are plotting these things, you need to get the entire xy coordinate for the whole. So to get the y value, you just plug the x value into your simplified function. And if you do want to write a note down right next to this, that this is going to be for rational functions only. Okay. 27 font, I'm going to use 27 size font. There we go. Then your vertical asymptotes. There are some other cases other than rational functions where these could occur. It's like logarithmic functions have a vertical asymptote where the inside would end up equaling 0. But I'm going to describe the vertical asymptotes where those occur for your rational functions. So it'll be where the factors left over in your denominator after the simplification equals 0. And then write a note to yourself that there are some other cases like log functions. Okay. For end behavior and horizontal asymptotes, that is just looking at the limits at the end of the functions domain. So let's say that your functions domain goes from negative infinity to positive infinity. You'd be looking at limits. The limit of your function as x goes towards negative infinity, and the limit of your function as x goes towards positive infinity. If your function's domain is broken up in between, but it still goes towards those same x values at the very end, that's fine. But let's say that it doesn't go towards positive and negative infinity. Maybe your domain is negative infinity to 5. So then you would just be looking at the limit as x approaches negative infinity for one of your end behavior limits. And then the other one would be x approaching, I think I said -5 or 5, but from the left. That's perfectly fine. We just want to know what's happening. And then for horizontal asymptotes, remember, those are just strictly if we have limits going towards positive and negative infinity, but it approaches a number. That tells me that the function is trying to level off at the very, very ends of the function. You have all of this information. You want to make sure that you plot any of the points or vertical asymptotes that you have, get an appropriate scale for your x and y axis, plot anything that you possibly can, and use all this information to sketch the graph. And if you are allowed access to a calculator, like on homework, make sure you check your calculator to see if you actually have a good sketch of your graph. But do keep in mind that the calculator, one, struggles with any log functions near its vertical asymptote, and it also struggles with actually showing you holes appropriately. So if you know where they are and you can zoom in enough, you can somewhat see a hole, but it is up to you to know exactly where it should be. I do also want to talk about the 4 basic shapes that we could get from our increasing decreasing combinations. So let's go with if you have a positive derivative and a positive second derivative. If you have a positive first derivative, or let's go with negative first derivative and a negative second derivative. Positive first derivative and a negative second derivative. And then negative first derivative, positive second derivative. I want you to sketch what these graphs would look like individually on your paper and then check back in when you're done. So pause the video now. When you're done, unpause it. So f prime being positive means that we are increasing. And f double prime being positive means that it's concave up. F prime being negative means it's decreasing, and f double prime being negative means concave down. F prime positive, increasing, F prime negative, concave down. F prime negative is decreasing, F double prime positive is concave up. So if I were to sketch an arc for each of these things, increasing and concave up would look like this. Decreasing and concave down would look like this. Increasing and concave down, that's not the best arc. Decreasing and concave up would look like this. Okay, so that is it for the note portion. Let's get into the example portion of the notes. 1, sketch the graph of f of x equals this rational function. So first thing that we're going to do, like I said before, is get the domain. And in order to get the domain of this kind of function, we are going to want to factor this. So let's see, numerator. I have to have a 2x and an x is my leading terms. And then that needs to multiply to negative 15. I've already done this before on my own paper, so I know that the factors are going to have to be 2x minus 3 and x plus 5. But double checking, I get 2x squared plus 10x minus 3x, which gets me my plus 7x, and then negative 15. In the denominator, x's need to multiply to negative 10 and add to 3. So that would be positive 5 and negative 2. So for my domain, that is going to end up being all real numbers except what would cause the denominator to equal 0, which would be negative 5 and positive 2. And I'm going to go ahead and circle that. Any of those key features that we discussed on the first page, I want you to circle those final answers, especially on your homework where getting all of this information plus graphing can get very cluttered. So if you just do that little extra thing for me, that would be super helpful. Plus, it'll help you when you're trying to find all this information when it comes to graphing. There is one more thing I'm going to do with my function, and that is I'm going to cancel out the x plus 5s. So now my new simplified function is 2x minus 3 over x minus 2. So for the most part, I'm going to be using the simplified function to find all the information. Okay, so next thing is finding critical points and then increasing and decreasing intervals, which means I need to get my first derivative. It's a little thick. Okay, I'm going to use that simplified function. And because it's a quotient, I'm going to use quotient rule. So we have low d high minus high d low over the square of what's below. So simplifying that numerator, I am going to distribute the 2. And multiplying by 1 doesn't really do anything, but I do need to distribute that negative. So we end up getting 2x minus 4 minus 2x plus 3 all over x minus 2 squared. Looks like the 2 x's will cancel, and we are going to be left with negative 1 over x minus 2 squared. Okay, so everything that deals with the first derivative, I will do below it. So critical points, first and foremost, how do we find them? Set our first derivative equal to 0, and then also look for where it does not exist. Okay, so setting the first derivative equal to 0. I'm going to go ahead and multiply the denominator to both sides. And we get negative 1 equals 0. That doesn't make sense. So that means that we are not going to get any critical points occurring from where the first derivative equals 0. So let's look at where our first derivative doesn't exist. because we have a rational function, that is going to happen where the denominator equals 0. So we get x minus 2 equals 0, which would be x equals 2. But remember, we have to check to see if this is actually in the domain of our function. This was actually one of our domain discontinuities, so that is not actually a critical point. So because we don't actually have any critical points, that tells me that we're not going to have any local extrema. Now I still want to go ahead and do my first derivative number line because I want to see where my function is increasing versus decreasing. But that just means that I only will see the domain discontinuities on my number line. Normally, remember, we want to see domain discontinuities and critical points. And you just want to make sure that you label the critical points if you have both of those things on your number line. But just in case it does change from increasing to decreasing anywhere, and you accidentally confuse those for local extrema, I would label -5 and 2 as domain discontinuities on your number line. And if disc doesn't do enough, you can say discontinuous or discontinuity. Maybe I'll do a little bit more than that. Here, let me fix it. There we go. All right, so I am going to test values in each interval. Let's start with -6. -1 divided by -6 minus 2 squared. So in the parentheses, I would get -8. When you square that, it becomes positive. So you have a negative number over a positive number, negative wins out. Now, because I have something squared in the denominator, my denominator, no matter what x value I plug in, is always going to be positive. Of course, other than 2, but that was a domain discontinuity in the first place. So with always having positive values in the denominator and always having -1 in the numerator, all of my intervals should end up being negative. So let's write our intervals of increasing and decreasing up. Increasing, that occurs where our first derivative is positive. That is not happening anywhere. Decreasing, literally the entire graph except for domain discontinuities. So you can either write up your decreasing intervals like our domain, just say everywhere except for x equals -5 and 2, or you can use your interval notation. I'm going to use interval notation. And then we have no local extrema. And I am making sure to write this that way. Let's say you take a break between doing some of your work and you forget that there were no local extrema, and you maybe accidentally in your sketch make it look like there kind of is one. You have this to remind you to check that you're not sketching one. Okay, so now that we have everything done with our first derivative, let's go into the stuff that requires the second derivative. And you have the option to either do quotient rule again, or if you want to bring the denominator of your first derivative up to the numerator, because I don't see any x's in the numerator, you could just use chain rule only. You'd have to use chain rule regardless with quotient rule, but if you just only bring the denominator up, you only have to use chain rule, not a combination. So that's what I'm going to do. I'm going to write it below where my first, where I'm going to do my second derivative, and then I'll erase it. To the -2nd power. All right, so let's go ahead and do my second derivative. So -1 times -2 x minus 2 to the -3rd power. That ends up getting me +2 in my numerator, and then I'll bring the negative exponent down. There we go. Okay, so let's go ahead and do everything that our second derivative will get us. So points of inflection and our concavity. Remember, to find points of inflection, that is where the second derivative equals 0 and has a sign change. So not only do we want to find a solution, but we have to test that on our our second derivative number line. All right, again, just like last time, go ahead and multiply your denominator to the other side. But also, just like last time, when you do that, you're really just left with the numerators equaling each other, or the numerator and one side equaling 0, which doesn't make sense. So that tells me that, again, there's no solutions from here, which, because this is the only way that we can get points of inflection, that tells me that there are no points of inflection on this graph. Now, that doesn't mean that the concavity doesn't change. Could change on either side of our vertical asymptote, because I know that we do have one. But the way that we figure that out, do your second derivative number line with those domain discontinuities. All right. So if I plug -5 into my, or I'm sorry, -6 into my second derivative, we get -8 cubed in the denominator, which is still going to be negative. We'll end up having a positive over a negative. Negative wins out. 0 would be a good number for my middle interval. 0 minus 2 is -2. -2 cubed is still going to end up being negative. So again, we have positive over negative. And then plugging in, let's say 3. 3 minus 2 in the denominator is 1. 1 cubed is still 1. So 2 over 1 is a positive value. So that's why I write domain discontinuities. That way I don't accidentally confuse them with critical points or points of inflections on whatever respective number line I'm working with, because you might accidentally confuse 2 in this case with a point of inflection, but it didn't come up from the second derivative equaling 0. It was just a domain discontinuity in the first place, hence labeling. All right, so let's write our concave up and concave down intervals. Our function is concave up where the second derivative is positive, which would be from 2 to infinity. It is concave down where our second derivative is negative, which would be -infinity to -5, and then -5 to 2. And then I know I already wrote down no points of inflection, but I'm just going to write that down one more time. Okay. So now with the final details, let's move into holes, vertical asymptotes, and behavior. There we go. So let's say that you are working with a function that doesn't have a hole. If you know that right off the bat, you could just write none right next to this, and it helps me know that you at least considered the possibility of there being holes before just shooting it down. However,
for this function, there is a hole. There was a factor that we were able to cancel out of the numerator and denominator. So x plus 5. Remember that equals 0 is a hole. Now remember, we are looking to end up plotting this, so we do want the y value for that hole as well. That way I can plot it like a coordinate. So I would go ahead and plug that into my simplified function, because if I did it in the original, it's just going to come up with 0 over 0. So if I plug that into my simplified one, we have 2 times -5 minus 3 over -5 minus 2 or plus 2? Minus 2. So that ends up being -13 over -7. However, if I'm plotting that, I have no clue where that is. So if I put that into my calculator, -13 divided by -7 is what decimal value? Looks like it's 1.86. So the coordinate for my hole is -5, 1.86. Right, next we have vertical asymptote. And those occur where any remaining factors left in our denominator equals 0. So the factor that remains in our denominator is x minus 2. Not that this requires work for you to say x equals 2, but that's where vertical asymptote is going to be. Lastly, end behavior. I think I need just a tiny bit more space. There we go. All right, so end behavior is looking at the limits at the ends of our domain. That's a little thing. So the ends of our domain happen to be towards positive infinity and towards negative infinity. And instead of writing the entire function out, I'm just going to write f of x. But because this is a limit at infinity and f of x is a rational function, I can use LERFT. So that it's really just the limit of the leading terms as x goes to infinity. The leading term in my original function f of x is 2x squared and x squared. However, you could just also use the simplified one since we do have that up there as what f of x equals as well. And we are left with 2. So it looks like we actually have a horizontal asymptote because our function is leveling off at an actual value and not going towards positive or negative infinity. And then if we look towards negative infinity, using LERFT again, it would be the exact same terms. So it would actually be the exact same limit. All right, so this would be our end behavior. Now, if you had a function who had a domain like x is greater than or equal to 0, then you would be looking at x approaching positive infinity and then x approaching 0 from the right. We do still want to look at either end of the function's domain to figure out the behavior there. So now that we have all of the pieces of information that we need, we are ready to sketch our graph. Now, in order to sketch the graph, you want to consider what is the range of x and y values that you have. That way you know how much of an x-axis to show, how much of your y-axis to show. But don't just look at the individual X and Y values, consider what they are and then going further than that. If I look at all of the various X values, it looks like I have -5 and 2 from the domain. And honestly, there are no other X values that popped up because we didn't have any points of inflection or critical points. So everything was kind of centered around those two X values when I look at everything that I've circled. So I think for the X axis, we want to go definitely double the distance from there. So like -10 and then maybe 6, -10 to 6. I know that's more than double of the other X value, but I'm going 5 to the left of my leftmost X value. We can afford to go at least 4 or 5 to the right. All right, and then for my Y values, looking at everything that we have circled, whole has a Y value of 1.86 and behavior is approaching a Y value of 2. So I'm not really getting too much happening in the Y axis at all. So let's at least go to maybe -3. And let's say at least 6. All right, so -10 to 6, -3 to 6. And also, I think scaling by 1 would be a good idea here. We don't really need to get too little on the decimal axis. Now, if we only had X and Y values within a very, very, very small range of each other, like we started having to break it down to like seriously decimal level, then we'd want to address the scale. But I think scaling by 1 is perfectly fine here. Okay, so let's go ahead and start with plotting our whole and our vertical asymptote. -5, 1.86, roughly right there. And then vertical asymptote at 2. Okay. And then we don't have any local extrema or points of inflection to plot. However, if we did have any critical points, like local extrema occurring or any points of inflection, you would want to get both the X and the Y coordinates for those. So from here, we basically get to move on to end behavior. Our function is leveling off at 2 on the far left and the far right. And let's see, if I go to the far left, because that hole is below 2, I'm going to assume that I'm going to be slightly below. I'm going to approach 2 from the bottom. And then I'm not sure for the right because I don't have any coordinates plotted over there, so I'm just going to go level with it. It is just a sketch. Now let's look at our intervals. Let's do the far left intervals first. All right, so I am starting off decreasing and concave down. So decreasing and concave down to 5. Not the easiest because 2 is very, very close to 1.86, but there is that slight curve down. And then after 5, between that and 2, I'm still decreasing and concave down. And because I have a vertical asymptote, as I get close to 2, I'm going to assume that it's going down towards -infinity. Because it wouldn't make sense to go up, then I would be concave up. Let's see what's happening on the right side of 2. Right side of 2 is concave up, but still decreasing. So if it's concave up, but decreasing, and I move from left to right, I'm going to assume that I'm starting at the top and then decreasing, concave down, leveling off at 2. So now that my sketch is fully done, let's take a look at our actual functions graph and see how close we were with our sketch. I'm going to type this in. I did alpha x just in case anyone has the newer calculator to fraction up, but I'm just going to pause the screen and the function will appear in just a moment. And then one more thing that I want to do is I'm going to change the window to what I have. Because if it was really far off, I definitely want to be scaled in a little bit. So we did -10 to 6. And then negative, I think I actually did -4 to 6. Okay, let's take a look at the graph. Hey, that looks really good. And then we could zoom into the coordinate -5, 1.86 if you really, really wanted to see if there's truly a hole there. We're going to zoom in. That's a little far. Let's see. Oh, too high. Sorry, guys. Okay. Oh, do you see that tiny little blip? With the cursor out of the way. There's a tiny little blip there, so there's truly a hole. All right, let's move on to our last example. Example 2, sketch a graph with the following features. Make sure to scale the graph appropriately. So I want you to look at all of the x values and all the y values and think about what a good range in both of the axes would be. So for my x values, I'm seeing 0, 0.865, 0.8650, 0. Okay, so I actually am not going very far in the x direction. In fact, with the domain, it goes from 0. So maybe I'll just go -1 to 2. And for my scale, well, actually, let's go -1, 2, 3. For my scale, I think I'm going to go by halves. And then, but I mean, truly, I think for that, you could do a whole number. It's up to you. Then for my y's, I see -13.6, infinity, 0, infinity. Okay. So I'm thinking maybe negative, considering this is from a local min and I'm not going very much lower than that, everything else seems to be positive. I think I can just go to -15 as my lowest one. I really don't need to go too much lower than a minimum. And then we'll at least go to, let's go to 4. And then for my scale, because that is such a wide range, I think I'm going to scale by 2s. I mean, it's not the widest of range, but that would get pretty annoying to scale by 1s there. So -1 to 3 and -15 to 4. Mostly negative. By halves for my x-axis. So I'm going to label that 0.5. Or I'm not even going to label the 0.5. I'll label the 1, 2, and 3. Two, 4. Let's see. -2, -4, -6, -8, -10. -12, -14. I guess we'll do -16. Since I'm scaling by 2s. All right. Go ahead and start by plotting any coordinates. So local min coordinate. No points of inflection. No holes. Okay, so just the local min. All right, so 0.658 and -13.658. 4, 6, 8, 10, 12, a little bit further. Okay. And what I do when I'm doing any local extrema is I will write local min or local max around them. That way, when I'm going to graph, I know that that's going to be like a turning point there. All right, so now let's see. No vertical asymptotes, no holes. So I'm not breaking up my graph at all here. Let's do the end behavior then. So we have nothing going to the left of 0 because our domain goes from 0 to infinity. So as I get close to 0 from the right, my function approaches 0. I'm thinking that that might be an endpoint. And it's defined as 0, so I think we have a hole there. Or not a hole, an actual coordinate. That's what I just said. And then as we go to the right forever, we're approaching positive infinity. So going to the right, top right corner, and draw an arrow up. Okay, so I'm going to start towards 0 or at 0 going towards the local min. It looks like we are decreasing and always concave up. Okay. So it'll go down, but it'll be curved up towards that local min. That's definitely concave up and it's decreasing. And then to the right of that local min value, the 0.658, it's increasing and still concave up. And there we have our graph, but I'm going to double check that everything is accounted for. Domain, yes, 0 to infinity. And the endpoint is defined, so we have the square bracket addressed. We have our local min plotted. Doesn't look like I have any local maxes, so that's good. Increasing and decreasing intervals are accounted for here. It's always concave up on my graph, so good. I'm not accidentally showing any points of inflection. My graph is never concave down. It's always concave up on that interval that's indicated. No holes, no vertical asymptotes. And if I do check my end behavior limits, as I get close to 0 from the right, my function is approaching a y value of 0. As I go towards infinity on the right side of my graph, my outputs are approaching positive infinity. So everything is taken care of here. All right. Oh, and then I guess I left a note. These are the graphical features of this function. Take a look at the function's graph and see how accurate your sketch was. All right, let's go ahead and do it. Nine x to the 7/3 minus 21x to the 1/2. That's where it's always nice if you have a function that you can compare with. And then let's see, we did for the x-axis, -10 to 6. No. We did -1 to, what was that? 3. And then we scaled by 0.5. For the y-axis, we did -16 to, I believe, 4. And then we scaled by 2. Hey, okay, perfect. That is very nice. That matches exactly what we drew. Okay, so the notes are done. If you have questions, make sure that you ask.